Good afternoon again. This is the second part of our meeting concerning the electric machine courses, the magnetic circuit. Today is 15th of August 2020. Okay, last time we stopped by this slide of the air gap, and we said that the air gap is the void, or is the air void found in the magnetic circuit. Why we find this void or this gap in the magnetic circuit? This is because of the rotative electric machines. The parts of those machines, stator and rotor, should be separated in order to ensure that we have movement or rotation. So this is why we have air gap in the machine. Also, we said we have shown an equivalent circuit of a magnetic circuit with the air gap, and we said that the air gap can be considered as a second material. So this magnetic circuit or this core will have a different reluctances for each material, the core and the air. And we show those expression of reluctances related to the core and the air. And at the end, we have talked about the side effect of the air gap, which called the Fringe of the flux. When an amount of the electric field lines or an amount of the flux will be spread out through the air gap, and that's why the area, the cross area of the core and the cross area of the air gap will be not equals, as we see here, due to this Fringe phenomenon. Let's take a pen. Okay, so here this is the cross area of the core, and this is the cross area of the air gap. That's why in many cases we should just neglect this phenomenon. Today we have an example may conclude what we have seen above about the magnetic circuit.
Sir.
Yeah.
Does it mean that the flux in the air gap doesn't equal the flux in the material, or what?
The flux, yes, if we consider that because the flux is related to the area, if we consider that the area are not equals, the flux is not the same. But if we consider the area is equals, the flux will be the same. Okay.
Okay, and if it is a small gap, so we will have the same flux.
Yes, we consider it as that we don't have Fringe phenomenon.
Okay.
Yeah?
Can I ask you another question, please? Does it mean also that the flux in the material equals the flux in the gap plus the Fringe flux?
Fringe flux, well, to be honest, I haven't seen something like this, how they can be calculated. Those it can be, I'm not sure, and I can't answer you, but it can be. But I haven't seen I have seen the similar case with the leakage and the linkage flux. Okay,
thank you.
Okay. So we have 42 participants, because هذه just بغينا نحكيو عليها that this phenomenon it exists, but generally we neglect it. Okay. Okay, so we have an example. Are you seeing the exercise?
Yes.
Yes, okay. So the figure 11 represents a magnetic circuit with a coil of 500 turns, and the mean core path, the mean length of we call it length or path, because it's the path of the flux, is equal to 360 millimeter. When the air gap length is 1.5 millimeter. Each, look here, we have 2 air gaps. Okay, we are seeing the magnetic core or the magnetic circuit with 2 identical air gaps. They have the same length. If the flux density, okay, so here when we have 0.8 flux density, the field intensity is equal to 510 ampere tour per meter. So firstly, they ask us to find the current in the coil. So راكم معايا? Are you with me? Okay.
Yes, yes.
Okay, good. So how we can find the current in the coil? We use Ampere's law. Let's go to the board. Firstly, the expression we are going to use is the Ampere's law. We know that the force or the MMF is equal to N times I. Number of turns multiplied by the current. So the current I equals to F over N. So this is the expression allow us to find the current. Let's see the presentation. Here how we can calculate F. So let's see the data. Here we have a magnetic circuit with different materials, of course, because we have an air gap and we have a core. So the expression of F, the MMF or the total MMF will be equal to the summation of the core MMF plus the air gap MMF. So F total here in this case, F total. So I'm going to write only expressions and explain. Then you can do calculation by yourself, or we can see it in the presentation. So F total in this case equals to F of the core FC plus 2FG, because we have 2 identical air gaps. So the total EMF equals to the core EMF plus the flux, the core EMF. You can see here that this is the core, and those are the 2 identical air gaps. So now let's try to find each one of them. The EMF, the MMF of the core and the MMF of the air gap. We know also, according to Ampere's law, that the MMF of the core FC equals to H, which is the flux and the field intensity HC of the core multiplied by LC. This is from Ampere's law. And also the MMF of the air gap FG equals to HG, which is the field intensity of the air gap multiplied by LG, which is the length of the air gap. So let's see what we have as a data in order to find FC and FC and FG. Yeah, we can see here that HC, the field intensity of the core, is given, and the length also is given. So this can be calculated directly. FC equals to HC multiplied by LC, 510 multiplied by 0.6 because we have 360 millimeter. In meter, it's equals to 0.36 and equals to 184 ampere turn. Now, the Fg of the air gap equals to what? Equals to Hg multiplied by Lg. Now here Hg is not given. So Hg in this case is not given. Hg equals to what? We use the expression of the density. Hg is B, the flux density of the air gap, over mu 0 from the expression of the density, because Bg equals to mu 0 over multiplied by Hg. So Hg is equals to Bg over mu 0. Why mu 0? Because here it's the air gap and we have only the air, which is equal to 4 pi 10 to the power minus 7. So here Hg, of course 2, because we have 2 air gaps multiplied by Lg, it's equal to Bg, the flux density of the air gap over mu. And so the air gap density is equal to the core, the air gap flux density is equal to the core flux density, because they have the same cross sectional. Okay, so we can see that have the same cross sectional, which is 0.8 over 4 pi 10 to the power minus 7. This is a constant value of the air. Why are the same? The flux density, because we have the same cross section. The flux related to the cross section. And the permeability of the air is a constant, of course, is given 4 pi 10 to the power minus 7. And the air gap MMF, the final value is 1910 ampere joule. Now let's go back to the current, the expression of the current. The current equals to the total MMF over the number of turns, which is F over N, and the result, as you can see here in the presentation. Now let's calculate the permeability of the core. Okay, so let's go to the board. Shall I clean this? The permeability of the core, we know that the relationship between H and B of the core BC equals to mu C, mu of the core multiplied by HC. So the permeability of the core equals to BC over HC. And those the values of those are given. So let's go back to the presentation. So here the permeability of the core BC is equal to BC over HC and equals 0.8 over 510 and equals to 1.57 10 to the power minus 7. This is the permeability of the core. And the permeability, of course, is equals to mu r times mu 0. The permeability of the air or of the free space multiplied by the permeability of relative to the material. So mu r here equals to mu c over mu 0 and equals to 1250. Yes, you see that there is a mistake. Yes, we have 2 here. 2 multiplied by Lg Lg equals to what? The value of Lg is given 1.5. Okay, yes, we should add 1.5. No problem, just you can check the calculation. Okay. Now, if the air gap is 0, if we don't have an air gap, if we don't have an air gap in this case, we don't have the MMF of the air gap. Okay, so if we don't have an air gap, so the current will be equal, so let's go to the table. Okay, we said that the current equals to total MMF over N. And this one equals to the MMF of the core plus the MMF of the air gap over N. If the air gap, if we don't have air gap, Fg equals to 0, of course, and the current will be equal to the MMF of the core over N. So this is the amount or the value of the current in case we don't have an air gap. Okay. If the air gap is 0, directly the current is equal to the MMF of the core over N. I hope that this example is clear. Yes. Is it clear? Okay. So we have directly, we have a lot of expression, I know, but all of them are direct application. We have a K expression. You should save in your mind. You see in this presentation all, yes. Sir, why does the flux density of the core equals to the gap? Yes, I said because they have the same cross section. Okay, if the cross section is different, they will be different. Okay, that's why, because the flux is the same. The flux is the same because it's considered as a series circuit. In the recitation, inshallah, we're going to see some cases when we have a parallel branches. Of course, the flux will be divided. Okay, and we will have different fluxes in those pieces of the core. But here is considered as a series circuit. The flux is the same. So if the cross section is the same, so the flux density would be the same. Now let's see another thing, which is the inductance of the core. Okay, so what is the inductance measured in Henry? The coil on the magnetic core can be represented by an inductance, which is defined as the linkage flux of the core per the unit current. What is the linkage flux? The linkage flux is the flux multiplied by the number of turns. So here you can see that we call it Xi, and in other books you may found it lambda or Xi. Xi or lambda is equals to the number of turns multiplied by the flux, and this is the expression of the linkage flux. So the inductance is defined as Xi, the linkage flux, over R. So this is the inductance of the coil. What does it mean, a linkage flux? I didn't explain this point clear in this presentation, I know. The linkage flux, the total flux in the core, in the magnetic circuit, can be divided into linkage flux and leakage flux. The linkage flux is the flux that kept in the core. So the flux that will be transferred over the core. You can see this picture here. The linkage flux is the useful flux. Okay, we can call it a useful flux because it's the flux that will be transferred in the core. The leakage flux is the flux that will be spread out ويضيع because leakage وش معناها فويت. Okay, so it's the flux that will be spread out in the air. You can see here, this one is the leakage flux that be spread out in the air, and the linkage flux is the flux that will be transferred over the core. So let's see, we can write it in the table that, okay, let's try to draw it here. We said that if we have, for example, a core like this is the core, and this one is the coil. This is the coil. Let's choose another color. The flux that will be transferred here into in the core will be called linkage flux. Linkage flux. It's a useful flux that will be transferred to another thing. For example, if we have transformer, this flux will be transferred to the voltage. If we have a motor, this flux will be transferred to torque or something like this. This is the linkage flux. The leakage flux is the flux will be spread out here. Okay, يعني الفلكس اللي راح يضيع في الهواء. Okay, so the flux, the total flux in the magnetic circuit is equal to the linkage flux plus the leakage flux. And sometimes we consider also this leakage flux, this leakage flux as we can be neglected, because according to يعني تشوفوا in the magnetic circuits, they try to do the winding يعني تكون concentrated to the core as much as possible, that we will not have a big leakage flux. Okay, so this is the meaning of the leakage and the linkage flux. The linkage flux is the flux, the useful flux that will be transferred in the core, and the linkage flux and the leakage flux is the flux that will be spread or disappear or something in the air. So this is the meaning of the linkage flux and the leakage flux. So let's concentrate with the linkage flux. The inductance of the core equals to, can be defined as the linkage flux over the current. So here, if we replace the flux by its expression, N L equals to N times phi over I, and equals to phi, of course it's BA, equals to N BA over I, and okay, they are saying that this meeting will be end in 10 minutes because we have only 40 minutes. I'm gonna share another link, okay? Yes?
Just enter the same link. I think it will work.
Really?
Normally, I think it will work. Just re-enter the same.
I will see.
Yeah.
Okay. If it's interrupted, I'm gonna share another link. Let's continue. So, and B is equals to mu HA over I. So here, just we do this substitution to find another expression to the inductance, and we see this term, all this term can be replaced by the reluctance, and the second expression of the inductance is L equals to N squared over R, which is the reluctance. You can check this by yourself. So the inductance can be found or can be determined from the linkage flux C over I, or can be determined from the reluctance N squared over R. And we have an example about this. So this is the second example. This is the second example. Okay, so one of you said that it works even that 40 minutes ended. Okay, great. Good news. Okay, so let's see this second example. So for the magnetic circuit shown in the figure 13, the number of turns is 400. The mean core length is 50 centimeter, and the air gap length LG is 1 millimeter. So you can see that we have also a magnetic circuit with an air gap. So we have, when we have air gap, we have different reluctances because we have different materials, as in the electric circuit when we have different resistances. So okay, the relative permeability of the core mu r is equals to 3000 and the current is 1 ampere. Find the flux and the flux density in the air gap and find the inductance of the core. So how we can find the flux and the flux density in the air gap? Okay, so let's go to the board firstly. So we know that the flux equals to what? Phi equals to the MMF over reluctance. And we said this expression is similar to the Ohm's law when the current equals to the voltage over R. So this would help you to don't forget this expression. So the flux is equals to the MMF over R, which is the reluctance. And in our cases, the flux equals to the total MMF, of course, over RC of the core plus RG of the air gap, because we have different materials. Then the expression of the reluctance, you can return to the previous slides. You can find the expression of the reluctance of the core. RC is equal to LC, which is the length of the core, over mu C, mu 0, AC, which is the cross section. And the reluctance of the air gap, G, equals to, yes, but how long does the air gap need to be for each area? I didn't get the question. Can you ask in the different way? How long?
Sir, she is talking about like the air gap, how much it needs to be big to consider it. Like when we put AC equal AG, we know when it is small, but how much it needs to be big to not consider AC equal AG.
Okay. So here in our cases, we are considered as the same. If it's not the same, you should be informed. يعني باللي it's not the same. But in general cases, let's consider them as the same to simplify those cases. Okay. هي الphenomenon, whatever the air gap is small, it will happen. يعني whatever. So let's consider it. We don't have Fringe phenomenon. Someone said that we have, we love the board. I love it too, but I hope that I can write with smaller size. But unfortunately, okay. So let's continue. RG equals to LG. Okay, sorry. Rg equals to Lg over mu 0, because we have only the A and multiplied by Ag. So those are the expression of the reluctance. I'm going to repeat. So the question was find the flux and the flux density in the air gap. So the flux is equals to the MMF over reluctance. This expression, as I said, is similar to Ohm's law when I equals to V over R. So in this way you can remind remember this expression. Now, since we have more than one material, we have the core and we have the air. So the reluctance, we have more than one reluctance. So F phi is equal to F over RC plus RG. And RC is equal to LC mu 0 times AC, and RG equals to LG over mu 0 over times AG. Okay, so let's go back to the presentation. Okay, this was the first. Okay, sorry, this one. So then we can find the density from the flux. When we determine the flux, we can determine the density from the flux. We have the expression that the flux is equal to phi over Ag. Okay, so this is the reluctance of the core, and this is the reluctance of the air gap. This is the result, because of course F is equal to Ni, number of turns, multiplied by the source current, because it's the total. This one is the total MMF. Okay, so the current here is the current of the source, of course, and the number of turns. So F equals to Ni over the summation of reluctances. So this is the result of the flux. Look, يعني calculation. Now we didn't consider the leakage flux. If the leakage flux is considered, I will tell you. Okay. So here we didn't talk about it, so we didn't consider the linkage flux. Good remark. Thank you.